All right. So in a previous module, we observed the moon at optical wavelengths. We made a color mosaic of the moon. In this module, module 1D, we're going to observe the planets at optical wavelengths. Now, at any given time of year, not all the planets will be observable. Depends on how close to the sun they are in the sky. If they're far from the sun, they're observable, but you can be too close to observe with the Skynet system. For example, right now, when I'm recording this video, Mercury's always too close to the sun. We'll never observe it with Skynet. Venus is usually too close to the sun, but every now and then it gets far enough away that we can observe it. But all the other planets, sometimes you can observe them, sometimes you can't. Like right now, I can't observe Mars, it's too close to the sun. But once every 2 years, Mars gets as close to Earth as possible, and it's opposite the sun. So it's once every 2 years, for a couple months every 2 years. Mars is a great target. Since it's so close, it's big, and we can see detail on it. Now, beyond that, you have the gas giants, Jupiter, Saturn, Uranus, and Neptune. And in this video, we're going to take a look at Jupiter, show you how to put an observation in of Jupiter, and then I'm going to do it again, but in a slightly fancier way. Okay, so let's see here. In this image, we have scale model, the sizes of the planets compared to the sun. Let me advance it one slide here. Take out the sun, here are the planets. So we're going to look at Jupiter. Jupiter, it's really big. It's the biggest of the planets. And also, at least compared to the other gas giants, it's a lot closer. So we can get a lot of good detail on Jupiter. We can get some detail on Saturn. You can certainly see the rings and some coloration on the surface. But Uranus and Neptune, they're smaller and they're far away. We're not going to see any detail, but our goal with these will be the colors. In fact, the goal for all the planets really is a study of their color. Also, I should point out, as we're observing the gas giants in particular, we'll see their moons. Here's a picture of the 7 large moons of the solar system. We have Earth's moon, which we are studying separately in 1A. It's really close to us, so we can do a mosaic and a really detailed job. You have Io, Europa, Ganymede, and Callisto in orbit around Jupiter. Those are the big 4, the Galilean satellites. That's pretty much all you're going to see in terms of moons around Jupiter. It has a whole bunch of small ones, but we won't pick those up. Titan around Saturn, easy to see. There are also some medium-sized moons around Saturn, very easy to see with Skynet. And then Uranus doesn't have any large moons, but it has a bunch of medium-sized moons, and you'll be able to see those. And then around Neptune, you have Triton, which is the smallest of the large moons, but very easily detected. And it's the only moon that we're going to see around Neptune. Okay, put the slides down. We'll come back to them. So I said we're going to look at Jupiter. So let's go through the steps here. I'm at Skynet. I'm going to go to my observatory. I'm going to add an optical observation. This is an optical observation of Jupiter. Adding a new observation. And we're going to look it up. Okay, found it here in the sky. Now, for reasons I'll explain shortly, all of our observations are going to be on the same telescope in Chile. Well, the Chile part I can explain right now. These planets, although they're big, all the gas giants are bigger than the Earth, for example, they're really far away. And so they subtend a very small angle in the sky. They're very small angularly. And the atmosphere blurs everything out over an arc second or more. At a good site, it's an arc second. At lesser sites, it could be 2 or 3 or more arc seconds. And if your target's already small, and then blurring it can just totally ruin any detail. So for the planets, we're going to just use telescopes or a single telescope at our best site, Cerro Tololo Inter-American Observatory in the Chilean Andes. there you have the best seeing, sub-arc second seeing almost all the time. So we're not picking our telescope here, but if you want to view the sky from Chile, here select Cerro Tololo, and you can see the sky. This is the sky right now. When you do this, it's bound to be different. This button right here is the now button. So the sun is still up, but it's setting. And there's Jupiter. I'll advance it an hour, 2 hours. The sun is set. You can see at the moment, Saturn, it turns out, is a little bit too close to observe. Neptune is barely observable if we play with the settings. But we have Jupiter, Uranus as good targets. And again, that's just for when I'm shooting this video. Every semester will be different. You have to play with this to figure out which planets are observable and which are not. In this video, I'm demoing Jupiter. So I selected it. Here are the coordinates. Max sun elevation, we'll set that to -12 for bright things like the moon and the planets. We could do -12. The sky is mostly dark. The pros don't start till it's down to -18. And for most of our deep astrophotography, we'll also wait for -18. But for this early exploration of bright, inexpensive, doesn't use a lot of telescope time, so it's inexpensive targets, we'll use -12. Min target elevation, you want to start by trying 30. If you want your target 30 degrees up or more, because then you're looking through less atmosphere. The lower you go, you're looking tangentially across the planet, you're looking through a lot of atmosphere, and that blurs your image. Now, sometimes we will have to go lower. I'll show you an example of that in a minute. But always start with 30. For these planets, we're going to start with min visible hours of 0.25. That's only 15 minutes, but for some of them, for example, in this case here, Neptune, I'm not going to demo it in this video, but it's only observable for a very brief amount of time, and we'll take what we can get. Even if we only get a few images, we'll take it and see what we can do with it. So I have this lower than normal. Max moon phase 100. We could do planetary observations even during a full moon. Now, bright ones, you can set the min-moon separation to 0. Jupiter, Saturn, Venus, Mars. They're so bright, you can observe really close to the moon. Things like Uranus and Neptune, you're going to want to give yourself some space. So if it's Uranus or Neptune, probably go with 30 here. Or if you just want to be safe, you could do the same. Now, right now, the moon is very, very close to Jupiter. And so if I leave 30 here, I'm going to have to wait. Let me move it forward like a day, for example. You can see the moon moved over here, got out of the way. Here, it's definitely out of the way. So if I leave 30 there, I'll have to wait probably 2 days for my observation to go through. So I'm going to set this to 0 because I want my data now. But Uranus, Neptune, definitely 30. So in the case of Uranus, I may have to wait a couple days to get my data back, given the current sky configuration. But we're doing Jupiter now. Okay. And down here, first of all, when you're observing the moon, we click this, the dithering, made a mosaic. We don't want that here. We're not making a mosaic. We're going to do a number of images, but they're all going to be right on top of Jupiter. So keep that unchecked. Here's another thing. With the bright planets, Venus, Mars, Jupiter, Saturn, Skynet will automatically add a 2 arc-minute offset. And the reason for this, bring the images back up, really bright things leave a residual in your image, a ghost, if you will. So remember, the light comes in, it strikes the sensor, knocks electrons into the wells of the sensor, and those electrons are then read out. But some of those electrons get trapped in the substrate of the detector. And they eventually go away, but it takes about 20 or 30 minutes. It doesn't matter how many times you expose. You can't flush them out. You just got to wait. And so what we're looking at here is a picture of a galaxy. This is in a narrowband filter, H alpha. So it's really just bringing out the star-forming regions of that galaxy. But clearly someone looked at Jupiter right before they took their picture. So it left a ghost here. Now, if you're doing astrophotography, that's really unfortunate. You don't want these ghosts in your image. We do have some ways to remove them if you take enough images, but it's not ideal. So when we put our planetary observations in Module 1D, we're going to use a telescope that is favored by the OPUS curriculum. The OPUS students observe a lot of bright planets, and there are thousands and thousands of them. So our preferred telescope here is Prompt 5. It's currently up and running. Hopefully it is during your semester. If not, Prompt 2 is a decent backup at Ceratololo. But we're going to, excuse me, still getting over a cold. We're going to use Prompt 5 because that telescope's already ruined with lots of residual images. There are a few telescopes that are really good for astrophotography, and I've taken them away from the OPUS users. The OPUS users don't see them. They're reserved just for the MWU curriculum, but we're not going to use those telescopes today either because we don't want to create ghosts in them. Now, the offset. Why the offset? Well, professionals also use these scopes. They're the primary users of these scopes. The education, we are fitting it around the professionals. You get to use the same scopes, the same system, but often they get priority. And often they're just looking at a single star, single object, and they'll put that object at the center of the sensor. So for these bright planets that leave a residual, we offset it. So yeah, it's in their image, but they're not trying to make a pretty picture. They just want to measure something they put at the center. And so it doesn't mess up their measurement. And that's why it's automatically offset, just so you know. Now, you don't have to set that. If you pick Jupiter, Saturn, Venus, Mars, it will put that there for you automatically. If you pick Uranus, Neptune, it'll change it to 0. Okay. See what else we have. Now, you want to come down here and check out the air mass chart. So prompt, the one that says prompt by itself is Tololo. If I click on it and blink it, there you can see it. And indeed, Jupiter is above that 30-degree mark for like an hour, hour and a half. Plenty of time. We only need to spend a few seconds, at most a minute, on this target. Okay. But if it were below the line, and it will be for some planets, you can come up here and lower this. I'll drop it to 20 just as an example. See, once you click off the box, it lowers the line. Now we have a longer window to observe, but your observation could take place at a lower elevation looking through more atmosphere. So only do that if you have to. We don't have to in this observation. We will in the next. Okay, that's good. Now we're going to choose our filters. With the lunar one, we chose the telescope first, but with most observations, probably choose the filters here first. And what filters to use? Let me come back here. I showed you this in a previous video. Most things that we look at in astrophotography, we're going to use R, V, and B for red, green, and blue. Kind of matches the human eye. We also have other filters called red, green, and blue that match the human eye even better. But often we'll use R, V, and B because we can calibrate it to astronomical catalogs more accurately. Anyway, with the moon was so bright we couldn't do that. Even at the shortest exposure times, the R, V, and B filters would let in way too much light and would saturate. And that's also true for the bright planets. For Venus, Mars, and Jupiter, it would saturate. So for those, we use the same trick that we used with the moon. We're going to use H alpha, O3, and U band, so we don't saturate. With Saturn, Uranus, and Neptune, we'll use R, V, and B. So here I want to deselect anything I have selected, and I want H alpha for red, O3. You can find them under narrowband or astrophotography, and U band under Johnson Cousins. If you come over here, you see it's marked out the telescopes that don't have those three filters. There are three pretty obscure filters, so you're going to lose a lot of telescopes. But as I said, we're going to be using the Prompt 5 telescope. It still has a green check mark because it has all three of those filters. Save and continue. Okay, this is the telescope page. I want to use the Prompt 5 telescope. Make sure I haven't selected any other telescopes, so just Prompt 5. Okay, save and continue. Make sure this is set to Prompt 5, not generic. And our bands are U, H alpha, and O3. You may have to set them. And then how many exposures in each band, in each filter, and how long do you expose in each filter? For that, go to the lab. Here's the lab, the module 1D. And you scroll down far enough, and you'll see two tables, Venus, Mars, Jupiter in one table using U, H alpha, and O3, and Saturn, Uranus, Neptune in the other table using B, V, and R. Okay, so we're looking at Jupiter. It says we want 10 exposures. We're going to image it 10 times. 1.5 second in U band and 1 second in the other two. You always got to look it up. Each planet has a different set. Saturn and Uranus, we need more exposures for reasons you'll see in the analysis. Okay, so I already have it in here. 10, 10, 10, 1.5, 1, and 1. Let me just double check. Yep, 10, 1.5, 1, and 1. It's good. Now, something else, when you come here, it will be on sequential. And that's what happened with the moon. It took all the red ones first, and then all the green ones, and then all the blue ones, or maybe some other order, but all of one filter, all of another filter, all of another filter. We don't want to do that here. We're going to switch to interleaved. This will rotate. It'll go red, green, blue, red, green, blue. Or in this case, it would do U, H alpha, O3, U, H alpha, O3. And the reason you want this is, what if you get cut off? Maybe you get through, I don't know, 7 of your 10 exposures, and then Skynet deems something higher priority. Maybe a star exploded somewhere, and researchers have a target of opportunity program, and they go over there. In fact, I should turn off my target of opportunity flag. This is an educational observation. I shouldn't be doing target of opportunity. It's very high priority stuff. Anyway, you could be interrupted, and your other observations, they may come back much later, and you can't combine them because the planet's rotating. After a couple of hours, even after 10 minutes, things are in different places. The red spot moves around, the moons move around. You need a bunch of data taken contiguously, back to back to back. So by interleaving, suppose you get interrupted, you at least get some in each filter. If you don't interleave, maybe you get your red and your green, but the blue was taken the next day. It's useless, and you can't make a color image. But if it's red, green, blue, red, green, blue, red, green, blue, you at least have some of each. Okay, so for the planets, be sure to interleave. Pretty much only for the planets. Okay. Save and continue. Then you submit it. It's in the queue. And as we've already discussed, you want to add this to your observation log and check back periodically to make sure the observations came out okay. Let me see if I have a completed Jupiter one here. Here's one. I'll open it up, and we can see there's Jupiter. It's been offset, and it's loading all the observations. Okay, now, what if I want to see the red spot? So this is for Jupiter only. For Uranus, Neptune, do as I described there, with the slightly different settings, as necessary. But Jupiter, Let's see what that's going to look like. Suppose that goes through first thing tonight. So let's go to Stellarium. Show you a little bit of Stellarium here. Loading. Okay. So once you get into Stellarium, first thing we're going to want to change the location. We are observing from Cerro Tololo. There it is, Inter-American Observatory. So pick the location, and you want to set the time zone to UTC. Because suppose at the beginning of the night we don't have a red spot. If we wait a few hours, we might have a red spot. And so we want to figure out a time that I don't want to observe before so I can see the red spot. And Skynet works in UTC, that's Universal Time Corrected, astronomical time. So change it to UTC, make sure daylight savings is off. Okay, all good there. Now, the next thing we're going to do, let's find the sun. Okay, it's getting pretty low in the sky. And I'm going to move time forward. If we come up here, date time, I can move time forward. Let's do that. Jumped an hour, another hour. So it's below the horizon, it's dark. The number I'm looking for, come over here and find as alt. The second number is the altitude. Remember, it does not start observing until, we set it to not start observing until -12. And actually, it's right at -12. Let me back up a minute. Yeah, we hit it perfectly. Right at this time, 0 hours universal time, 47 minutes, sun will be low enough at Cerro Tololo to start observing. And there's no guarantee that our observation will be first, but let's see what it would look like if it is. So I'm going to search on Jupiter now. And as I said, right now, for me, it's very close to the moon. When you do this at some later date, it probably won't be. But Jupiter's so bright, should be okay, even that close to the moon. So I zoom in here. I can see the 4 Galilean satellites, Io, Europa, Ganymede, Callisto, and there's Jupiter, and the red spot is not facing us. Here's a nifty little trick. Come down here, click on the telescope icon, flips it around. This is the orientation of your camera. Your camera's riding on the telescope. The telescope's working in the RA-DEC coordinate system. And so this is now in equatorial coordinates, right ascension declination. Your image will look like this. Sometimes it's a flip or a rotation, but pretty much like this. Okay. So that observation we just put in, if it goes through beginning of the night, that's what it looks like. Let's see how high Jupiter is in the sky. Go up here to altitude 40. So we said, as long as it's above 30 degrees, and this is at 40, so this might very well be what comes back. Damn it, I want to see the red spot. So let's move time forward until I see the red spot. Let me zoom in a little bit. Oh, there it is. I suppose whoop, must have set. Let me back it up an hour. Okay, so let's see. The altitude here, 2152. Now, I said we're only going to observe if it's above 30. So we'll submit another observation, and this time we'll lower it down to 20. So we can actually see this. So let's back it up a little bit. Let's try 2 hours, 40 minutes. It's an altitude of 23. Want to get a few degrees above so I have time to collect all my observations, all my exposures. We did 10 exposures. That usually takes a minute or two. And this gives me enough time. Maybe I'm not going to get the telescope exactly at 240, but hopefully I do before it's set below 20. Okay, so this would give me the red spot, and the moons have moved around a little bit, but not too much. So let's try this. So it's, for me, it's January 19th, 240. I don't want to start the observation before. So function F11 to minimize stellarium and get rid of it. I'm going to come back up here, my Jupiter observation, open it back up again. And I'm going to resubmit it. I'm going to go back to the beginning here. So the target is Jupiter, -12. And we learned we have to lower this now. I'm going to lower it down to 20. Min visible hours, I don't know why this resets. I'll just put it back at the 0.25. 100, 0, that's all good. It's what we had before. Dithering off. So if we look at the air mass chart here, find prompt. There it is. So, Jupiter is well above for a long period of time, but we're not going to observe until 240 universal time. It's probably somewhere right around here, right before it's going to set. Choose filters, should still be UH alpha 03, save and continue. Choose telescope, but still prompt 5, save and continue. This check, make sure that's set to prompt 5 and not generic. Here are the exposures that we put in before. They've already interleaved them. So down here it now says sequential. We can leave it at that because they actually have them in here 10 times interleaved. When you pressed interleaved, it changed your request to do UH alpha 03, UH alpha 03 over and over and over again. So you only see that on the resubmit. You're doing this the first time and you're going to do 10 exposures, be sure to interleave them. But if it's a resubmit, then you don't have to interleave. But we do have to delay. And so our delay time was January 19th at 2:40. So delay the start of the observation until then. Doesn't mean it's going to happen then, but it's not going to happen before then. So hopefully it will happen right around then. We'll get the red spot. If not, it will set and it will execute anytime the next day. In fact, you should come back and check. And if you didn't get it, cancel it, resubmit it, upping it a day. Okay. Save and continue. Submit. There we go. Okay, that's doing planetary observations in Skynet. And again, not just a single exposure. We did multiple exposures because we're going to stack them for a number of reasons. We'll get to that in an upcoming